Hi everyone, welcome back to the cardioid simulation series, where we explore math and physics visually and interactively. In this episode, we are diving into two powerful vector operations, the dot product and the cross product. These are not just formulas, they are tools that help us understand alignment, forces, rotations, and real-world physics. I have prepared some awesome animations and examples to make everything super clear. So let's get right into it. First up, the dot product. The dot product is a way to measure how aligned two vectors are. Let's say we have two vectors, a yellow vector that stays fixed and a red vector that we rotate around it. Watch how the dot product changes as the red vector rotates. When the two vectors point in the exact same direction, the dot product is at its maximum, in this case 9. As the red vector rotates toward 90 degrees, the dot product decreases until it reaches 0, when the vectors are perfectly perpendicular. As the red vector continues rotating past 90 degrees toward 180 degrees, the dot product becomes negative, meaning the vectors are now pointing in opposite directions. So what does this tell us? The dot product is all about alignment. When dot product is a big positive number, it means vectors are pointing in the same way. And when it's 0, it means vectors are perpendicular. And when it's negative, it means vectors pointing opposite directions. Here is a cool example. Imagine a light ray hitting a flat surface. When the light hits the surface straight on, that is perfectly aligned with the surface normal, the dot product is high, and the light intensity is maximum. Our little sphere here glows the brightest. But when the light comes in at a sharper angle, the dot product decreases and the light intensity fades. This is how lighting works in computer graphics and in the real world. Here's another one. When you push an object like this block, the useful part of the force is the part that's in the same direction as the displacement. If you apply a force that is angled upward while the block moves to the right, the dot product helps us figure out how much of your force is actually moving the block. We calculate the work done using the dot product. Watch how the block moves based on this calculated work. Dot product is everywhere, in physics, engineering, and in game physics. Now let's jump into the cross product. The cross product gives us a new vector that is perpendicular to both of the original vectors. We have a vector A in blue pointing to the right, a vector B in red pointing straight up. When we take the cross product of vectors A and B, we get a new vector shown in green that points perpendicular to both, pointing in the Z direction. This is how we calculate directions in three-dimensional space. Here is a physical example. When you apply a force to the end of a lever, the lever rotates, and the torque is the cross product of the lever's position vector R and the applied force vector F. Watch how we calculate the torque vector T. When the lever rotates counterclockwise, the torque points up, and when the lever rotates clockwise, the torque flips and points down. This is exactly how torque works in real world, whether it's turning a wrench, opening a door, or pedaling a bike. Here's another beautiful example. Angular momentum. We have a position vector R in blue pointing outward from the center, a tangential position vector P in green moving around the circle. When we take the cross product of vectors R and P, we get the angular momentum vector L. As the object moves in a circle, the position vector rotates and the tangential vector changes the direction, but the angular momentum vector stays perpendicular to the motion. And this is how planets orbit, wheels spin, and pretty much all the rotational motion works. And that's all for this episode. I hope you learned something new. If you enjoyed this, don't forget to like, subscribe, and hit the bell icon so you won't miss what's coming next. Until next time.